And welcome to the Winds and Currents webinar. Today we have Ernesto Rodriguez from JPL, who's going to talk about the technical aspects of Doppler scatterometry, the physical basis, and the performance and trades that are necessary to think about a satellite mission. So I'll let you go ahead, Ernesto.
Thanks, Sarah. And I want to emphasize, first of all, that this is for the purpose of discussion. So not only do we want questions from you, we're asking questions of you because you're helping define the mission, and there are trades that are open that we need to hear from you. The second thing is, it is not a mission yet, so the instrument is in an evolving state. A lot of the performance may depend on the budget or the things that are not yet decided. And so what we're going to do is give you a range of possibilities. So what I'll do is I'll start with why we think this is going to work in terms of the physics of the measurement, what the mission is going to look like, how well will it work, and then some questions to discuss there. And I hope to be done in less than half the time allocated so we can have significant time for discussions. I'd like to acknowledge my partner in crime on this is Alex Whitehier. We've been working on developing Doppler scatterometry for winds and currents now for half a decade or so, or a little bit longer for me. So with that, let me start. So the problem that altimeters have, or SARs, is that they measure very precisely over a very narrow area. Scatterometry was really a breakthrough in this, in that it enabled, by using pencil beam rotating antennas, to cover the entire world within one day. And that really starts to get at the fast phenomena that we want to map. And fast phenomena are also coupled with smaller spatial scales. And so we want to go explore the limitations of where we can go in temporal and spatial scales with a mission that improves both by an order of magnitude relative to current altimeters and continues the scatterometer constellation. So the physics of the measurement is fairly simple and well established, at least in some regime. For the winds, we use scatterometry. So there's a relationship between the magnitude of the radar return and the wind that is forcing the Bragg waves that respond to that wind. And those are what the radar is sensitive to. The one issue that we will be looking at here is that traditional scatterometry has happened at lower frequencies, either KU or C-band, and we want to push to another frequency so we can improve our temporal, our spatial resolution. So we want to go to Ka band, which is about 8 millimeters of wavelength. And the new aspect is the Doppler aspect. We use something that's very much akin to a police radar, where you send out pulses and you take a look at the phase difference between subsequent pulses and relate that to how much whatever it is that you're looking at has moved. So this has been used by the police for decades. I think they use LiDARs nowadays. And it's also the basis between for something like the HF radars. It looks very, very similar to that. One of the advantages that the scanning architecture has, the pencil beam architecture has, is that you can get front and back looks at the same spot. And that allows you not only to get the speed, but it also allows you to get the full velocity, two-dimensional velocity component, both through winds and from currents. So there is some magic that happens between the raw radar measurements and the physical measurements. For the winds, there's something called the geophysical model function that has been used now for decades that translates backscatter cross-section to wind speed and looks at the modulation of the backscatter cross-section to get the direction. On the left, you see you have some fresh off-the-press results from Federica Polverari et al. Based on a tower experiment at Ka band, where we looked at how the backscatter cross-section varied as a function of wind speed and direction. And we compare against some older results collected in a Black Sea tower by Yuri Yudovsky and collaborators, both using Ka band. The two data sets have pretty good agreement among themselves. And so we think that Ka band does have the sensitivity to retrieve winds. And to show that, on the right is some data collected using the Doppler instrument, which is an airborne instrument that demonstrate this as a function of time, where we flew the instrument over in the Gulf of Mexico, over an eddy region, and we compared against NDVC and another platform, the Buoy-Fugro platform. And you can see that as a function of time, the retrieved winds agree very well between the truth in the platforms and what the Ka band can see. Similarly, for the currents, in this case, the measurement is much closer to the physical quantity. We measure the velocity of waves. The problem is, how do you relate the velocity of those waves to a surface current? And so those waves are getting advected by the surface currents. And the hope is that if you average over a lot of waves, the wave velocity will average out, and you will just be left over with the surface currents. Unfortunately, for physical reasons that I can get to into discussion, the averaging process does not average out all the radial velocity of the surface waves. And so another geophysical model function, which depends on wind speed, must be used in order to reduce these wave effects. And what you see on the left is the setup that we had as part of the ACID experiment, part of the ESMO mission, where we collected Ka band radar data over multiple azimuths over more than 3 months. And we're able to derive these geophysical model functions, which are shown on the right. And the plots on the right are basically 5-minute averages of radial velocity as a function of the relative direction between the radar look direction and the wind direction. And you can see the signature, that's residual motion from the waves. Basically, when you have a 0, those are waves coming towards you. And when you have plus minus pi, those are waves moving away from you. And you can see there's a contamination in the upwind and downwind directions. But it's fairly well behaved. So these are just the raw 5-minute averages without any fitting of the data. And you can see that just averaging over 5 minutes, which is equivalent more or less in averaging in space over 100 kilometers or so, you get something which is pretty consistent. One of the issues that has been raised is whether the physics of this geophysical model function depends very much on other things than wind speed. Here, we've separated things in terms of wave age into young, equilibrium, and old oceans, and you can see that there's no evident trend between those. So we can use these geophysical model functions in order to retrieve the currents. On the left, we have comparisons against ADCP measurements, and basically we show that we have unbiased results with pretty good correlation. On the right is some examples that we collected over an eddy in the Gulf of Mexico. And we're comparing here against optical measurements derived by looking at surface wave dispersion by an instrument called ROCUS from Fu Group. Basically, that instrument forms spectra, space-time spectra of waves. And by looking at the Doppler shift relative to the dispersion relationship, you can estimate the surface current at a couple of meters, average over a couple of meters. And you can see that there's pretty good agreement between the U and V components as you cross the eddy boundary, although there are some differences that will need to be understood as part of the geophysical model development. And finally, some hot off the press results. This is some during the ESMO, which is NASA Earth Ventures suborbital 3 mission. Tom Farrar is a PI. These are 4 different days of comparisons against another optical measurement of wave current Doppler. This is from Doppler, an instrument whose PI is Luc Lenin from Scripps. And what you can see is that after tweaking the geophysical model function, there's a pretty good correlation between the U component and the V component. The wind speed and conditions vary significantly over these data collections. And these are the type of measurements that we hope that eventually get from space. These are quick look results during the ESMO campaign on the left of wind vectors, wind speeds, and on the right of surface current. And then you can see a front there. And then you can use those for the currents and measure the relative vorticity and divergence. And I have plots here, relative vorticity over the Coriolis parameter for our location in the California current system. So you can see that this is pretty promising in terms of identifying regions of dynamical interest. So how do you go from an airborne system to a spaceborne system? Basically, we keep everything the same as much as we can. Just raise the altitude from about 10 kilometers to about 650 kilometers, and keep the incidence angles to where we understand the measurement physics. And that allows us to have large swaths on the order of 1,700 kilometers or so. And that allows us to have nearly daily sampling. The other thing that is quite different between the airborne platform and the spaceborne platform is that the airborne platform, we can get away with a relatively small antenna, 20 centimeters, and relatively low power transmission on the order of 100 watts. For the spaceborne platform, we will need something which has a long, skinny antenna. And I'll tell you why we need that. But this is basically on the order of 4 meters in length, whereas the QuickScat antenna was on the order of 1 meter. And we need more power. So we will be using 400 watts as opposed to the QuickScat power, which is 100 watts. So both of these are more expensive, but not extraordinarily so more expensive. This is not in the same realm as a SAR system. So as you know, a bunch of us have been putting together the outlines for what we think a mission would look like. And Sarah is our PI, and Fabrice Ardouin is our French lead, and we have a very strong US-France partnership in this. We've had to make some compromises in the mission already. We wanted to start with a 3 AM, 3 PM terminator orbit to complement the ASCAT constellation the best that we could, but because of power requirements, we had to go to a 6 AM, 6 PM, but we're keeping the wide swath. So at 650 kilometer orbit height, we get 90% global coverage within 1 day. And we're also using a 4-day repeat cycle in order to be able to have validation. Many places will be sampled twice per day. The exact swath width is actually being optimized because there's a trade between measurement accuracy that determines the instantaneous accuracy of the instrument and temporal sampling. And so we need your feedback on this. The spatial sampling that we're keeping is better than 5 kilometers. The instrument is a K-band Doppler interferometer with a single rotating beam antenna. This is in contrast to QuickScat that had to have 2 beams. We can get away with a single beam because we combine the Doppler for direction and the K-band for radar cross-section. And we plan to have a data latency less than 6 hours to enable near real-time oscillations. So using it for ECMWF or using it for Navy models. This is a typical example of what the coverage will be. There will be some variations in this depending on the swath that we pick, but within 1 day, we will get basically global coverage with some holes, and many of these places will be covered at 6 a.m. and at 6 p.m., so twice per day. Very much like the QuickScat coverage performance. I don't expect you to read all these things, but we have 3 levels of mission that we're looking at right now. What we're calling the nominal mission, where we think we can do the science that we can validate easily. A gold mission, which is if everything goes right with the engineering, we think we'll be there. And a threshold mission, which is if everything goes wrong, and we're forced to cut back, this is how we will do in terms of performance. And I noticed that I forgot to copy over the threshold requirements here. So I will update that and send it around. But basically for wins, we have something that is very similar but better than the QuickScat requirements. The QuickScat requirements were 2 meters per second speed and 20 degrees. We have more like 1% of wind speed or 1 meter per second, whichever is greater, and 15 to 20 degrees wind direction, depending on the wind regime. We think we can make that even smaller, as you can see in the gold mission. If you look at the velocity performance, the velocity, the 2 components of the velocity have very different performance characteristics, as you can see on the plot on the left. So the along track component is very well determined at near nadir, which is 0 here. Far swath is 1. So this basically replicates on the other side of the swath as well. So that has very good precision there and poor precision in the far swath, whereas the cross-track component, because of the measurement geometry, has poor precision in the near swath and much better precision in the far swath. And then if you combine those, you'll have a sweet spot in the middle where the speed will have almost constant precision, and you'll have increase in the speed accuracy on both sides. So for the mission, we will collect all the data, but and we will be reporting the components for over the entire swath. But for many applications, we will be looking at just the sweet spots area and exclude a small area in the center and a small area in the outside. And this is where these requirements hold. So the nominal mission, basically, we hope to have a speed accuracy of 35 centimeters per second when sampled at 5 kilometer pixels. And since most of this is random noise, this translates to about a 7 centimeter per second at 25 kilometer resolution, 25 kilometer sampling. And you can see that the component accuracies are on the order of 25 centimeters per second at 5 kilometers and 5 centimeters per second at 25 kilometers. Our goal is to reduce things basically by 10 centimeters per second. And our threshold is, can we live with something which is 50 centimeters per second at 5 kilometers, which translates to 10 centimeters per second at 25 kilometers. So all of these are pretty abstract because you really, what you can do with these type of things depends on the application that you have. And a lot of looking at the application and the trades that you go from space and time averaging have been looked at by Dudley, Shelton and company in this paper that I put in here. And a lot of the results that I'm going to show you are from that. So this is for the California current system. These are the results from Dudley simulation of the resolution. And what you see in red is the signal for the kinetic energy, basically, spectrum. And on the first slide is what happens when you average spatially to 20 kilometers. In the middle panel is when we average to 50 kilometers. And in the far right panel is what happens when you average to 80 kilometers. And what you see is that as you average, you're averaging the signal, but the noise averages much faster than the signal, so you can get improved resolutions, improved spatial resolution of the wave number of the features that you can resolve in the ocean. So the top set of panels are for the kinetic energy, basically, the speed, and the bottom set of panels are for the much tougher measurement of relative vorticity. And you can see that initially you can't see anything at all, but as you average over spatial scales, you start to resolve the relative vorticity. So that was for the California, so in Dudley and company's paper, they looked at the resolution capabilities, both in instantaneous measurements and as you average in time. So on the left, you see snapshot resolutions in terms of the wavelength, and I won't have time to go into detail what that means, but basically it's a signal to noise ratio in the spectral sense of 10 between the kinetic energy, let's say in the velocity, and the noise. So this contrasts to the requirement in the SWOT mission where they have a ratio of just 1. So it's a pessimistic assessment of what the resolution is. See instantaneous, and then as you average over 4 days and 14 days, you can see you can get much better resolution. So the top level, the top panels are for kinetic energy, the lower ones are for relative vorticity. Alex Pointier, Hector Torres, and I did a study for various regions that had more kinetic energy than the California current system. And we did similar plots here. And you can see that in energetic regions, like the Gulf Stream region, you can get resolutions for, it depends on the wind speed, but you can get on the order of tens of kilometers, and relative vorticity and divergence on the order of 30 kilometers or 30 to 50 kilometers for the divergence. So I would say that goals of in energetic regions of having a goal of resolution of 25 to 30 kilometers is feasible, but it'll be harder in less energetic regions. So this is a hot off the press simulation of global estimates of what the kinetic energy resolution with a signal to noise ratio of 10 in the global sense is. So bluish things are where you're resolving things at scales of less than 30 kilometers. Green are between 30 and let's say 60 kilometers, and you start to get yellow as you get from about 70 to 100 kilometers. So you can see that you have very good resolution in the energetic regions in the western boundary currents in the Southern Ocean, but along the equator, but in areas with a lot less dynamics, your resolution is not as good. You may have to deal with on the order of 80 to 100 kilometers. This is for an instantaneous plot of resolution. So you will do much better if you average temporally over a repeat cycle or so. So the error sources, we have several error sources. We have random errors, which basically we will average out as you average spatially. And those depend on the antenna width. And then some that depend on the square root of the transmit power. So we're less sensitive to the transmit power than to the antenna width. We have errors in the pointing, and I'll go through those very quickly. Some of them are high frequency, which we can measure with an inertial reference unit, and some of them we need to estimate from the signal itself. And finally, we have errors due to the geophysical model function not being quite right. This is similar to the EM bias in altimetry, introducing errors at long wavelengths, which are the scales of the variability of the winds. And we expect that these systematic errors will be improved as the mission continues, the same way that the EM bias has been improved in altimetry as the mission continues. Strangely enough, compared to altimetry, the errors depend mostly on the wind speed, but have very weak dependence on the significant wave height. The errors due to the Doppler variability can be explained in the following way. Suppose that you're looking at a footprint, so you're flying along from left to right, and you're looking at a footprint looking to the side. So when you're looking straight across, you have 0 Doppler shift. When you're looking forward, you have your blue Doppler shifted. When you're looking back, your red Doppler shifted. So when your footprint has a large variability in Doppler shifts between blue and red, it's like a policeman looking into the highway with traffic coming towards him and traffic going away from him. What is the average speed? So clearly that's going to be the noisiest measurement. Typically we get a cross-section along a range slice indicated here by this gray thing. So this is our largest error. When we look back or forward, we're consistently either redshifted or Doppler shifted, and this is where our lowest errors are. And so that's why our performance varies significantly between the near swath and the far swath. Right now, we're thinking of going between a 3 to 4 meter antenna, and that makes a different, basically a 30% difference in the performance. So we hope that we can keep the 4 meter antenna, but that will depend on the cost. The other significant error source is the pointing. If you don't know which way you're pointing, you can't ascribe your velocity to a velocity vector. And so basically, that's linear in the pointing error, and it gets multiplied by the velocity of the platform. In this case, the velocity of the platform is about 7.5 kilometers per second. And the accuracies that we want to get are in the centimeter per second region. So that means that this delta phi has to be on the order of microradians. Luckily, technology in terms of gyros is now at a stage where we can measure microradians. So in the right, we see what the translation between microradians and centimeters per second is going to be. So right now, our goal is to have 15 microradians accuracy. That translates to a 10 centimeter per second random error. The capabilities of the gyros right now are here, so much better than our requirement. And the stream, which was a European proposal, looked at this and they had a requirement which was like this. So we're being a bit conservative relative to stream in allocating our errors at this stage. So to close this, there are some issues that where your input would really be useful. So temporal sampling versus measurement noise. If we bring the incidence angle in, we'll have a smaller swath, but also the signal will be brighter and your noise will improve. However, you may get fewer than 2 samples per day, and your ability to resolve things like near inertial oscillations may suffer. So the question to you is, what is the right trade between instantaneous noise in both winds and currents and temporal sampling for your application? The other issue is, as Dudley and Company showed, you can get significantly better resolution if you do spatial averaging or if you do temporal averaging. And so we need to drive the noise level either by either one of those to something where you can resolve the features that you're interested in. If you look back at the plot that I showed you globally, that resolution will vary significantly depending on where you're on the ocean. What does the space and time resolution need to be for the application that you're looking at? Another issue here is absolute versus relative currents. Some of these errors, like the geophysical model function errors, will have very long wavelengths. So if you look at things on a scales of 30 kilometers, when you compute the relative vorticity and the divergence, the error is due to these absolute error biases will basically go away. If you're looking at contrast, if you're looking at a thing where you're driven by a relationship between the contrast in the wind and contrast in the currents, like the coupling that Lionel talked during our last meeting, you care much more about relative winds than about absolute winds. So the issue is, do you need absolute winds? Do you need absolute accuracy for your application? And at what scale do you need them? We need to justify our mission. So what science can you do with a threshold mission, with a baseline mission? Do we really need to meet the goal mission? And as you saw, we can now get global simulations to estimate things like what the scale of resolution is, in this case for the instantaneous shot. And we're engaged with some of you in doing simulations to try to see what the accuracy will be at different noise levels for your applications. We'd like to hear from you about any applications where we could do an OSSI to find out how our mission would perform and get the right trade between space and time sampling. And with that, I think I'm done, and I think it's time for questions.
Thanks, Ernesto, for a great talk. Are there questions? Well, maybe while people are thinking, I'll ask a basic question. You just showed this great map showing the scales that are potentially resolved. How is that defined as a scale? Are you thinking of that as a wavelength or a?
Yeah, this is the criterion proposed by Dudley, Shelton and Company, where you have a spectral signal to noise ratio of 10 between the filter signal and the filtered noise. This is a fairly conservative estimate. As I mentioned earlier, SWAT uses a ratio of 1 rather than a ratio of 10. And we're using also a conservative filter, a partisan filter, which Dudley advocated. And as Dudley pointed out, if you use something like a Lowe's filter or other filtering, you can get a significant reduction. But basically, this should be viewed as the wavelengths at which you can resolve the spectrum of your application.
Thanks. I see that there are hands up and people ready to go. Let's start with Lionel Renaud.
Hi, Ernesto. Thanks for your talk. Very nice talk. I just have a comment about your last slide and the need of relative or absolute wind. So one application among many others could be to force an ocean model with the wind, actually. But for that, we do need the absolute wind, because when we want to take into account the current feedback effect on both the large scale and the mesoscale activity, we need the absolute wind. Otherwise, we won't have the effects on the eddies. We could have it using a parameterization, but in that case, we may have an issue with the large scale effect, the slowing down of the mean circulation, by double accounting it. So to me, it's very important to have absolute wind, at least to force.
Yeah, that's a very good point on the stress, Lionel. If you look at our requirements, right now our requirements are an absolute. So I feel that the scatterometry part, the wind speed part, and the part that has to do with the stress is fairly, in a good basis, will be at a better performance because we have much better spatial resolution than the QuickScat mission, and at similar noise levels as the QuickScat mission, or better noise levels than the QuickScat mission. If you look at in terms of things like wind work, we have a stress dot tau. Certainly, the biases will contribute a bias on the wind work, but a lot of the wind work, what you care about it is the variability. So some of the results that have been presented have to do more with variability. But yeah, our intent is to meet both absolute and relative, but we'd like to find out which applications are impacted by going to one or the other. And certainly driving models with relative winds is not good. You need an absolute stress to drive the models.
Thanks.
Can we go now to Megan Cronin? Megan, do you want to ask, or should I read your question?
I'll ask the question. So these surface currents from space have the potential to save lives, and especially in small island developing states. And so would you be able to do an Aussie in that kind of situation? I would think it'd be very complex. Some of these, small island developing states have multiple islands, clusters of islands, and so a lot of topography. And can you speak towards that? And also, I want to plug that tomorrow we're going to be having OASIS is going to be having a UN Decade Laboratory virtual workshop, Air Sea Observations for a Safe Ocean. And I put in the chat how to register and get the information or call-in details and the GatherTown links and stuff for that. Hope to see you there.
So, excellent point about the coastal applications. Part of our NOAA colleagues, as part of the science team, ones around, have emphasized that nowadays the coastal applications, not only for islands, but also on the US coast are driving what NOAA is doing. So one of the things that we were very careful is to try to keep the spatial resolution to 5 kilometers. And so when we get 5 kilometer averages, we actually will be able to measure currents at 5 kilometers. But they will be noisy, and you may be able to average but there are currents, for instance, between the Big Island of Hawaii and some of the other islands that should be resolvable. So I think maybe we can start with Hawaii as a test case, if you think that's a good case, because we have some ground truth there, some coastal radar, and I think it would be exciting to do a simulation there. So thanks for the suggestion.
Yeah, that's great. Let's go to Shen Elipo.
Hello, hi Ernesto. Thank you very much for this presentation. So did you say that the requirement on the uncertainty for ocean currents is on the order of 20 centimeters per second? Is that what you had in your table, I think? Is that the right order?
So let me go back. It depends on how much you want to average, obviously.
Okay.
So at 5 kilometers, the nominal emission will have 35 centimeters per second, 1 sigma accuracy. If you average to 25 kilometers, that'll be on the order of 7 centimeters per second. On the component scale, when you average to 25 kilometers, you're looking at 5 centimeters per second on each of the components.
Okay, so yeah, so because I have to admit that looking at the 25, 35 number, I was a bit, disappointed in the expectation because, from like the historical drifter data set, typical values, the most common values or like the median values is between 20 and 30 centimeters per second on hourly time scale. So
Yeah,
that's something
understood. So it's doing things from space is a lot harder than doing things when you're there.
Sure.
But I think that, so that's where the trade in applications and the spatial averaging required for applications. This is not a mission to examine the sub-mesoscale between 10 kilometer and 30 kilometer, I think, but is more looking at the short mesoscale and other processes.
And so I have a follow-up question. Should we expect correlation in the uncertainty between winds and currents?
No. So that's one of the great things about using completely different measurements. The winds use the backscatter cross-section, which is the power, and the currents use the phase. And so the error is between the two of them are correlated, but the standard deviations of the currents depend on the wind speed. So the variance will depend on the wind speed, but the mean does not depend on the wind speed.
Okay.
So you get noisier measurements the lower the wind speed is, as opposed to some of the other instruments where you get noisier measurements the higher the wind speed is.
Okay. All right. Thank you.
Thanks. Let's go to Gérald Dubabor.
Hi, thank you, Ernesto, for this very interesting presentation. My question was related to your last slide. When you asked the question about resolution and averaging, whether it's in space or in time, maybe a good way to approach it would be to provide some Stroman values, for instance, 2 or 3 scenarios that the science team could examine, and give you some feedback based on a limited set of options as a starting point.
Yeah, we're working on that, Gérald, rather than having a continuous set of options. So right now, we'll follow up with a more concrete set of options that we're looking at. The options will probably depend on what the payload capabilities are and the nominal orbit that we're looking at. But I think just in terms of temporal scales, one of the things to look at is instantaneous measurements. So basically sub-daily or daily versus averaging over one exact repeat cycle, which would be 4 days for this mission. So that would be one thing to think about. One repeat cycle, 4 days, is still a factor of 2 better than the repeat cycles for the altimeters. And so that's one of the things to keep in mind. But thanks for the suggestion, Gérald, and maybe we need to keep track of what the community desires are in order to make some of these scenarios.
And in order to empower the science team to look into this topic, I would suggest to have a very simple simulator, such as the one that was developed for Scheme Stream or even SWOT, in order to have simulated data sets with typical configurations that we can compare, so that we compare things that are comparable.
Yes, and Alex Weintier has built just such a thing, and it's available to anybody who wants it. It's Python code, and we're also running things for people when don't have the knowledge or the time to run those. And so this is an example of such a simple simulator run globally using the MIT GCM couple model runs. So we look forward to suggestions. We can either share the code, or so you can run it on your models, or we can actually run some of these things if we have enough time and not too many suggestions.
And if I can interject, if you're thinking about doing this, this is exactly the time to do it while we're building the case for writing a proposal. Once NASA comes out with the final call and people are in mad proposal writing mode, it'll be harder to take in new information, but now is the perfect time. Let's go to Larry O'Neill, who has a question in the chat. Larry, do you want to read it, or should I?
I can do it. Hi, Ernesto. I was just wondering if there's any prospect that surface current measurements within the swath, if they'll always have a nadir gap, or if there's any prospect that that can get closed up.
So thanks for the question, Larry. So you will have very good measurement of the along crack component, as you can see in this figure. You know, basically, it'll be an order of magnitude better than the speed measurement in the middle. Given the geometry, so you have a very good measurement of the V components of the current, and we plan to report both components throughout the entire swath. The U component, the errors will be significantly higher, as you can see there. And so, you know, this is one of the areas where science team processing and science team ideas of how to optimally use data that has unevenly distributed errors to get the optimal maps, maybe by doing some optimal averaging, or maybe by doing some dynamic averaging that takes into account the relative errors between U and V components in an optimal way. But that's certainly an area where we're looking for ideas from the science team.
Okay, thank you.
And let's go to Dudley now.
Hi, Ernesto, could you go back to the slide of the kinetic energy resolution map? Yeah. So do you have any ideas of why the resolution is poorer in the tropical Atlantic, particularly the South tropical Atlantic? You know, what's the process that's responsible for that? That kind of surprises me.
It surprised me as well, and this is hot off the press at 11 p.m. by Alex Weintier last night. The answer, no. But having maps like this, I think, really is important to try to investigate what's causing problems like this, or issues like this.
I think that the eddy kinetic energy is low in that area, and it may just be that you don't have much of a signal power, but I don't know. Yeah.
So we really need to take a look at that. You need to understand these maps.
I wanted to make one other comment too. Earlier question was whether this resolution is, you know, what this is the resolution of. I think Sarah asked that, you know, and you said it was a wavelength resolution. Just for comparison's sake or reference sake, if you want to think about that in terms of the radius of features that can be resolved, it's about roughly a factor of 4 smaller than a wavelength resolution. So if you had a wavelength resolution of 80 kilometers, say, then that would be equivalent to being able to see the radius features with radii of about 20 kilometers.
Thanks, Dudley. I wanted to be conservative like you, and not mention that, but I'm glad that you're being the one that's being a liberal and casting an optimistic aspect on this. But yeah, these are very conservative estimates of what the resolution is going to be. And we will put out some other maps with other estimates, like the different spectral regimes, or something like the feature resolution, or the radius resolution that Dudley mentioned.
Thank you.
Greg Jacobs has a question in the chat. Greg, do you want to say your question?
Oh, sure. Ernesto, you pointed out there's a number of different error sources from the sensor itself to movement of the satellite. And I was just curious what the relative amplitudes are and what the characteristics of the correlated errors are.
Yeah, excellent question. So I should have put that there, but the bottom line is we're governed by the random radial velocity errors due to the footprint size. So this is our dominant error source. This one, the one in the azimuth, only affects the cross-track component, and typically it's on the order of 10 centimeters per second. So if you look at the total RSS over here, if you subtract 10 centimeters per second in an RSS sense from these numbers, you'll get to see what the random error due to the footprint size is going to be. That's why we've been pushing so much for a large antenna, which is rather costly. And so that's one of the major traits in the mission right now.
Great. And then Clement Umelman has a question in the chat. Clement, do you want to ask?
Yeah. Well, one was a comment on about the simulator that, yes, it would be great to, I think, ask both the code to be able to run it on any model, and also to be nice to get the sample if it's already done on the LLC. Because well, we plan to try the work we did with Kim to map NIOs. We did that in the North Atlantic, and I was wondering if the simulator was available, the simulated data were available for LLC in this region.
Absolutely, Clement, and we're looking forward to sharing things with you and others. You know, it's a very simple simulator in the sense that, what it does is it doesn't reflect the spatial structure of the simulation, and it doesn't reflect the distribution of wind speeds. It just reflects the science requirement rather than the performance. But that's good, because if you can show that you're under the science requirement over your entire footprint, you're much likely to be better as the wind speed increases. But again, it's a conservative simulator.
So far there is a random noise only, right? At these levels, and I guess we can play with that. And ideally, we would have maybe to play with, as Gerald said, two configurations, like one with a larger swath, but different noise and so on, just to be able to find this trade that you mentioned in your last slide. So,
absolutely, and we'll take the action to limit the scope. I didn't want to limit the scope initially because I didn't want to be technology driven, but rather science driven, and hear back from you what you can do. But I understand that it's easier when you have a smaller menu.
Okay, great. Yeah.
Well, we are just about at the end of the hour, and there's a lot of food for thought. Unless there are other questions, I think we'll just thank Ernesto and leave everybody with this charge to take advantage of the resources available and give us feedback on requirements and science that could be done, and what you think the trades should be. So,
and Sarah,
thanks.
if you could just stop the don't quit yet. I will share my presentation. I will put a link in a second. So just give me a second to put a
Okay.
link in there.
Well, meanwhile, a round of applause.
Okay, anybody can have the presentation if you look at your chat, and we'll also distribute it on email.
And I'll put it up with the recording as well. So thanks very much. And thanks everybody for joining us.
Bye, everybody. Thanks for listening.